Welcome to this new season of the lecture series of the Network for Ocean Worlds. This network has been formed by NASA to advance comparative studies to characterize the Earth and other ocean worlds across their interiors, oceans, and cryospheres. In particular, the studies investigate their habitability, the search for biosignatures, and try to understand life in such environments. In this third season, we investigate in 4 episodes how we can explore ocean worlds through analogs. This second episode focuses on laboratory studies, which are presented by 2 speakers. First, Xinting, planetary material scientist at the University of California, Santa Cruz, will present how she investigates the material properties of organic liquids, ices, and hazes on Titan in her laboratory. Then, Paul Johnson, planetary scientist at the Jet Propulsion Laboratory, will show how he is studying frozen brines in the lab to get insights into Europa's surface chemistry and microbial viability.
Thanks. And I know, so what I found out is that planetary materials and their property also matters for various atmospheric processes. For example, cloud formation, cloud haze interactions, etc., etc. But today I want to focus on Titan, of course, my favorite planet, planetary body in the solar system and outside the solar system, I think. All right. For those of you who are not familiar with the Titan, Titan, there are so many cool things about Titan, but I think one of the coolest things is that Titan is actually the only moon in the solar system with a substantial atmosphere, okay? But if you look at Titan in visible light, this is all you see. It looks like a giant yellow ball without much feature, so you can't really know what's going on Titan's surface by looking at it visible light. So what is happening in Titan? So we know that Titan's atmosphere is actually pretty similar to Earth. So the dominant component similar to Earth is nitrogen. So Titan's atmosphere is made of about 95 to 98% of nitrogen, depending on where you look in the atmosphere, and a few percent of methane. Again, depends on where you look. But we don't need much methane to actually make very interesting components in Titan's atmosphere. So in the upper atmosphere of Titan, we have UV photons from the sun and energetic particles coming from Saturn's magnetosphere keep heating these atmosphere molecules. And that leads to very interesting photochemistry happening in the atmosphere, making a variety of simple gas-based organic compounds. So just to date, we actually have detected at least 17 gas-based simple organics. So these are all the things I love since high school: unsaturated hydrocarbons, nitriles, all these organics. And in addition to forming the simple organics, once these simple organics are formed, they can further polymerize and coagulate, and somehow form larger in size and also chemically more complex solid phase organic particles. So we believe Titan's atmosphere is full of these micron-sized organic particles that we think actually form the thick haze layers that we see in the atmosphere. And the reason Titan looked like a giant yellow ball is because these haze particles are opaque to the visible light. So instead of seeing what's going on the Titan's surface, we're seeing these haze particles instead. And on the right, you can see this limb image of these nice haze layers in Titan's atmosphere. And to make things a little bit more complicated, these simple organics, once they're formed, because they're heavier or denser than the background atmosphere, they'll eventually fall towards Titan's surface. And actually, if you look at Titan's temperature pressure profile, there's a temperature inversion. So that means at some point it's getting really cold in the atmosphere. So that means when the simple organics when they're descending through the atmosphere, they'll get cold trapped. So that means they would likely condense at some point when they're descending toward the surface. So that leads to phase change. So that means these gas-based molecules will at some point turn into either liquids or ices, okay? And I told you there are at least 17 molecules that have been detected. And if we plot something called the condensation curves of all these 17 molecules, we'll find here, so basically the solid black line is the Titan's temperature pressure profile, and all the colorful lines condensation curve for each species. So whenever you have a colorful line intersect with the black line, that means this material is condensing around that altitude and temperature. So basically, the general idea of this plot is showing you everything would condense at some point in Titan's atmosphere. All right, and we actually have detected some of the direct evidences of this phase change happening. So we have seen clouds made of various compositions in Titan's atmosphere. For example, here I'm showing you a hydrogen cyanide cloud hanging out in the southern pool of Titan. But in any case, okay, we have these simple organic molecule, gas-based organic molecules. They turn into liquid or solid phase at some point in Titan's atmosphere. And these organic hazes that are more complex and already solid when they're formed. And all these materials would fall towards Titan's surface, okay? And because we get a mission that's going to arrive in 10-ish years, we better figure out what material we're going to expect with Dragon and Fly, and also their relevant property related to the space mission. So that leads to us to actually compile some of the properties that are of interest. And during this whole process, actually lasted for like a few years in my group, there are lots of trouble doing that. And it's a different problem for these two substances. So for the simple organics, people have been studying simple organics since, over 100 years ago. So it's not like we don't have data. It's just the data is they're almost like too expensive of the data. So we're talking about data that exists in literature for actually over 100 years. And you really need to know what's already there to figure out what we still need to do, like what gaps we need to fill in. While for the organic hazes, it's a different problem, which I'm going to explain a couple more slides later. But I just want to show you guys the product already to see, like, to show you guys what we have been doing in the past few years that has finally have the product online. So we made this material property database for all relevant organic liquids, ices, and solids on Titan. So we just took a few generations of undergraduate students to help with me. But we currently, the current website you can access through this QR code. And I also have the paper, which is still currently in revision, dropped on the archive. But we have thermodynamic properties, physical properties, surface properties, and some electrical and optical properties currently summarized and up there for you to use. I just want to highlight some of the properties that took us a lot of time to configure, and just to show you kind of what we have. So we think we have the first time a complete set of saturation vapor pressures for all the 17 Titan relevant simple organics. So apologize for showing you this huge long table. You don't need to look at any details. But I just want you all to pay attention to the temperature column. So again, this is the saturation vapor pressure expressions for all these simple organics on Titan. So for this temperature column, as you might have noticed, there's some temperatures that are in brackets, while some are not. So whichever temperature in brackets means the relationship is extrapolated function. So that means we don't have any laboratory data. So I really want to point out this temperature column because this means proposal opportunities for lots of you here. So we really need lots of low temperature saturation vapor pressure measurements. And for some substances, we have nothing. So we have to use some other thermodynamic data to do our best guess to calculate their possible saturation vapor pressure. Another compiled data set we're really proud of is we think we have the most complete density data for all the Titan relevant simple organic ices. Okay, so it's very easy to use. You just plug in a temperature and you get a density at a certain temperature. So note that this is the material density of all the ices. So it's the maximum density you can have for this ice. And if you're adding any porosity, you just have to plug that in, and which will reduce the density. But again, if you look at the temperature column, again, lots of proposal opportunities out there. Some of the ices have either just one measurement or no measurement at all with their density. All right, so I talked about the simple organic database we had, and for the complex organics, the problem is we have too many labs. So what does that mean? So I want to just note to you all, I think all of you know that to date, we have not had a sample from Chatain yet. Okay, there's no sample from Chatain. So how do we even study these complex unknown organic hazes on Chatain? So experimental people turns out to be quite smart. So even though we can have no access to samples, we're like, how about we make their own in the lab? So the idea actually have started a few decades ago. And basically, what we can do in a laboratory setting to mimic Chatain is, how about we start a gas mixture that mimics Chaitain's atmosphere composition? And then we expose the gas, just like the atmosphere chemistry happening on Chatain, to a similar energy source that Chaitain's atmosphere gas being exposed. For example, we can use a UV lamp to simulate UV photons from the sun, or we can use another energy source called the cold plasma to simulate energetic particles from Saturn's magnetosphere. But in case, in this laboratory setting, we can also mimic this chemistry, and that leads to a material that's produced on Earth as an analog of Chatain hazes, which was named Stolling by Carl Sagan and his colleague Bishop Carey, who invented this material. But I would say one of the prevailing questions of the Chatain Stolling community is that we don't really know if any of these Stollings produced actually now from multiple laboratories actually equals to the real hazes on Chatain. So basically for the modelers, if you're seeing these papers published from different groups claims they make Stolling and measure some of their properties whatsoever, claims this is equals to the same thing as the real hazes on Chatain, okay? And that's a real problem because we really don't know if that's really the case. So just to give you an idea of why that is the case, so here I'm just choosing 3 laboratories that are actively producing Stolling, and I listed some of the relevant experimental conditions that each lab used to produce the material. And for example, you can see some of the experimental conditions they used to produce Stolling actually varies by orders of magnitude. Okay. So I think the way really to figure out this problem is, how about we gather all the possible materials from all these different laboratories, and we measure all of them using like a standardized approach. So even though everybody's sample is made differently, they get to measured using the same approach. So we're getting really comparable data. And then we can try to use some of the existing Cassini-Huygens data and all even future dragonfly data to figure out which experimental conditions or even which setup makes small analog that's closer to the real hazes on Chatain, so we can study then more properties starting from there. So this effort actually started during the pandemic. And we're been using haze samples from these 3 laboratories, and we're recently funded by the NASA Cassini Data Analysis Program to keep doing this collaborative work. So how this works is, again, basically all the lab produces their own samples, and that's the only difference we're having. And then these samples are all transported in a standardized approach, which actually I'm working on with my student Eric White in the lab. So we have 2 transportation vessels, a vacuum vessel and a dry nitrogen vessel. So the samples are never exposed to air. If you remember vaguely, the Chatain hazes are made with nitrogen and methane, so there's no oxygen. That's the reason we never wanted the sample to expose to air. And then all the measurements are done in an inert atmosphere in my lab. So here, just a setup I made during my postdoc at Santa Cruz with my postdoc fellowship. Simple setup to measure the surface properties in the atmosphere with some Home Depot gears. All right, so during the pandemic, we launched our first pilot study of this comparison study. with 7 soiling samples produced from these 3 different laboratories. And there are many cool things we found out from this comparison study, but just want to highlight a few things. So we measured this property called surface energy, which is an indication of how sticky this material is, okay? And you can also separate the surface energy into 2 components, so the dispersive component and the polar component. So that tells you kind of the bulk chemical composition of the material. So basically, if you get a very high polar component, it means lots of the bonds in this material dominated by there are a lot more polar components, or like a polar compounds overall in this material. So the first thing we found, there are 3 things we found are quite interesting. The first thing is, well, these samples are different, but it seems like there's some experimental condition that matters more than the other when producing these samples. So especially the 2 samples that are made with far UV lamp, so FUV shown here, despite all the other experimental conditions vary hugely from each other, somehow we would produce the solings ending up with similar surface energy. Okay, so so it seems like the energy source is the dominant condition that matters for the surface energy of the material. And the second thing is now instead of providing one number like the previous studies for modelers to use, we're now really considering the variability of soiling properties because everybody indeed produce somewhat different material. So we're really encouraging people in the future to consider this variability because we don't know which sample is the best analog of Titan's actual hazes yet. To use a range of possible numbers in their future modeling to consider this uncertainty. And the third thing is you're like, okay, all these samples are different. Now we're just like, we lost all clue, right? But the good thing is there are indeed some common properties of all the samples. So even though the total surface energy is quite different between all the samples and polar components are different, it seems like all these samples tend to have pretty high dispersive surface energy component. So, you know, given that all these samples are made so differently and they somehow all have this property, we would think the actual hazes on Titan may likely also have this common property. So we should be more confident to use such common properties to in theoretical studies to make conclusions about actual surface and atmosphere processes on Titan. And as I told you, we are just funded to keep doing more properties with this collaborative approach, and we'll welcome more labs to join this effort. Feel free to let them talk to me and see how we can have you all joining this collaborative effort. And the eventual hope is with this property to be measured, we would like to compare it to the existing data and figure out what kind of conditions would make better analog of soiling. And again, all these data are actually archived in the material property database. And the idea of having the website database, even though the papers are published, we can still keep updating the database to reflect the newest literature from the laboratory studies for both the simple organics and the complex organics for Titan. And we have been using this database ourselves to do some theoretical work. For example, my group are interested in cloud formation on Titan. So we've been trying to understand how do we form these various hydrocarbon nitrile clouds on Titan. So as you might have heard of on Earth, if there's no aerosol, we would have no clouds. What it's telling you is that you don't really form a cloud by condensing material and it grows by itself. The most efficient way to form a cloud is you cling to another particle and you grow on top of that. So that saves you a lot more energy. So we're trying to use our database of the complex organics and the simple organics to investigate how various hydrocarbon nitrile clouds form through heterogeneous nucleation. So we kind of tested how classical nucleation theory affected hydrocarbon nitrile cloud formation with all these data we have from the database. So here on the y-axis, I'm showing you the critical supersaturation that's needed to form a cloud. So nothing fancy. Basically, the higher the critical supersaturation you need from a cloud, it is harder, okay? And then, we calculated the kind of cloud forming efficiency of all these weird hydrocarbon nitrile clouds. And then we're actually able to compare to what Cassini has observed in Titan's atmosphere. And what we found is basically what we predicted with classical nucleation theory, at least, really doesn't match what we have seen in Titan's atmosphere. So there's some cloud that, based on theoretical predictions, very hard to be formed, but we have seen them. So it tells us, we're still actually trying to figure this out, but it tells us either it's the classical nucleation theory is wrong, or there might be some other seeds other than soling that can nucleate the cloud better. And some other theoretical project we're working on with this bit database includes what's the fate of the simple organics and the complex organics when they landed on Titan's surface. So if these organics landed on a dry surface, we want to figure out, do they land up as a liquid or solid or gas? So that will really help us understand what kind of material Dragonfly expected to encounter when it landed over there. And while if these materials landed on a wet surface, so for Titan, if they landed on the hydrocarbon lakes, we want to investigate what's the fate of these materials. We're wondering if whether do they dissolve into the lakes or do they float or sink into the lakes. You might have wondered, why does it even matter? Why do you care if they float or sink? So in 2019, actually, I didn't put a citation on. There's a paper talking about how do we possibly explain why Titan's Lake is so weird. So Titan's Lake is actually ghostly smooth. So we're talking about wave with amplitude less than 1 millimeter. Okay, so that's crazily smooth. So that paper by Caldier and Carrasco talked about maybe we could have a floating layer of substances. So just like when you have an oil spill on Earth's ocean, which we know actually dampens the ocean waves, maybe we have a floating layer of something on Titan's lakes that dampens the wave. That's why Titan's lakes are super smooth. So that's something we're actually actively working on with these databases as well. And another thing, just want to jump in to say that some side project we're working on, as some of you might have known soling or worked with soling, we can't really produce it in large quantities. So whenever you ask the lab, I want 500 grams of soling, they'll be like, oh no, it's impossible. So during my PhD, the lab I worked with at Johns Hopkins actually was one of the most productive labs. And we make less than 1 grams of sample for every whole 3 days of experiment, okay? And to date, we still don't have a Titan analog material made in large quantities. That really creates a problem for the community, because if you look at other planetary community, the moon people have their own lunar soil simulant, the famous GSC1. Now, the Mars people have their simulant. The asteroid people now even have their own simulant. But actually, what we've been using for Titan as a simulant is crushed walnut shells. So you can ask me why we use that. But in any sense, in 2019, actually before COVID, I was visiting this scientist called Julie Brissett at University of Central Florida, and I was talking to Julie, and it seems like she's just like me. She's also a planetary material scientist, but Julie only do measurements in large quantities. So she had this huge shear box and a drop tower, and I was like, I couldn't work with Julie really. I've never had enough materials for her to work with. But then I was like, actually I've measured all the material properties of soling during my PhD. We have all these material properties. How about we make a Titan simulant together? So that conversation actually ended up being pretty nice. And we decided to write a proposal together that got funded. And we were actually able to persuade some material scientists to actually make this material for us. So the goal of the Titan simulant is we do not want to mimic its chemical properties, okay, because it's toxic. I don't work with soling in large quantities really. And we really want to mimic soling's material properties. And we want it to be able to be produced in large quantities. So we're currently at the stage of we can produce hundreds of grams of this simulant within a day. So that's pretty wonderful. But we're still fine-tuning its material properties to mimic soling. And the goal is to have soling to be this analog to be able to be used by people who do book scale measurements, such as Julie, who can use a drop tower. And we should be finally able to mimic actually some of the measurement that was done by Huygens more than 10 years ago, but finally with the right material. And Dragonfly has been using some of our simulants already, so really excited about this material coming up. And then I just want to make some advertisements of my upcoming lab, hopefully at UT San Antonio. I'm hoping to make a standardized planetary material characterization facility. I've been working a lot with aerosol analogs, but I'm hoping to work with more materials to come. But if you have students that are interested in doing this, there are lots of things we can do, but we are hoping to do more of these cross-laboratory comparison for soling to provide these kind of large community accessible databases. And so people can use it to understand various atmospheric and surface processes on Titan and beyond. And we really hope to support future missions in that way. And I'll leave my final slide for any questions you might have. And if you have any students or interested in applying for grad school, please have them reach out to me and apply to UT San Antonio. Thank you so much.
Thanks, Xinting. Wonderful talk. Now we will have Paul Johnson from JPL. Paul got his PhD in Canada at the University of Manitoba before coming to JPL as a postdoc, and is now the Deputy Manager for the Planetary Sciences section. And he's going to talk about some of the surface chemistry work with relevance to Europa. So take it away, Paul.
Okay, well, first of all, thank Aaron for inviting me to give the talk. Basically, I'm going to be talking about a number of experiments we've done over the last few years where we've looked at frozen brines that are relevant to Europa. The work I'm going to show is basically done in collaboration with Matthew Choukron, Robert Hodis, and Tuan Vu. And as I get towards the end and start getting into some microbiology stuff, that'll be work that's involved Tae-Woo Kim and Seth Parker, and all of us are at JPL. All right, so again, for this crowd, Europa really doesn't need a whole lot of introduction or motivation, but I'll just touch on a couple points that are relevant to what I'll be talking about. Of course, one of the main reasons why we're so interested in Europa because of its potential for habitability, or it may be even the potential that there's life in the ocean. And this comes about because we think Europa has all the ingredients that we need for life as we know it, right? There's a global saltwater ocean in contact with the rocky core. We expect all the chemicals we need for life to be present, either from formation or delivery from impacts. And the radiation environment and hydrothermal vents that we think are on the seafloor could be providing the energy needed for life. The other point that's relevant to what I'm going to talk about is the fact that the surface is very young. The lack of craters implies a surface that's 60 to 100 million years old or so. And if surfacing is occurring on a regular basis, then we have this kind of intriguing possibility that the ocean material could be expressed on the surface where it would be more easily examined. Okay, so the composition of the subsurface ocean is, of course, interesting both in terms of geochemistry and potential habitability. The combination of surface observations by things like Galileo's NIMS instrument, along with geochemical modeling, suggest a range of possible ionic compositions for the ocean. But how can we learn more about the ocean? Well, there are, in fact, various technologies currently under development, hoping to access the ocean directly. But until I think that we could all sort of agree that, at least in the near term, our understanding of the ocean is going to be largely limited to what we see on the surface. Future missions like Clipper that will be getting there hopefully soon, and concepts like Europa Lander have actually aimed to study surface compounds and try to make these links to ocean composition. So the idea being that if you'd have a remote or in situ identification and quantification of surface minerals, you use some understanding of physical and chemical changes that occur as a brine is frozen and placed on the surface, and use that to infer what the composition of the initial brine was. And the experiments we do help hopefully try to understand this bit in the middle. So where did we start? Well, we want to keep things tractable and simple, so we considered a simple putative ocean brine containing sodium chloride, magnesium, and sulfate ions. We do a bunch of experiments where essentially we freeze brines under different conditions, concentration, cooling rate, etc., and then examine what forms upon freezing and after the ice is cooled down to 100 Kelvin, which we sort of use as our representative surface temperature. So the first work we did along this line was published back in 2016. Here we were looking at slow freezing of several sodium, magnesium chloride, and sulfate brines. Basically, these experiments involved putting aliquots onto a microscope slide in a cryostage, cooling those down slowly at 30 Kelvin per minute down to 100 K, and then looking at samples with Raman spectroscopy. Here's a picture of the instrumentation we use. This is a LabRam HR confocal Raman microscope. All the experiments that we I'm going to talk about here were done with the green laser, the 532 nanometer laser. And you see here on the cryo stage underneath the microscope, and off to the right, it's this pump and some control electronics that then pull liquid nitrogen from this dewar through the cryo stage, and that allows us to control sample temperatures. Okay, so sorry. So the first experiments we looked at were looking at one-to-one volume mixtures of saturated sodium chloride and magnesium sulfate solutions. And playing around with this, we see formation of hydrated sodium sulfate, mag chloride, sodium chloride, but we don't see evidence of magnesium sulfate in those experiments. So we had this question: is the fact that we have excess sodium biasing formation of mirabolite? So we then started to play with reduced sodium brines. And in these experiments, we're still seeing preferential formation of hydrated sodium sulfate and magnesium chloride, even when we had elevated magnesium to sodium ratios. And this has this simple experiment has kind of a potential impact or implication in terms of epsomite on Europa. Now, epsomite is a mineral that has been suggested to be present on Europa, but if the source of material looks like the brines that we were playing with, then the presence of epsomite would require a very sodium poor ocean in order to form on the surface, or in order to form. Or another possibility is that a radiolytic process converts mag chloride on the surface to epsomite. And I should point out that this is an idea that was proposed in 2013 by Brown and Hand, where they suggested that sulfur coming in from Io would convert the mag chloride into epsomite on the surface. So the next thing we started doing was trying to understand this a little better. So we began mapping out the sequence of mineral formation from these brines as they cool and freeze using a chemical divide model. And then we did a bunch of experiments trying to see if this model's predictions were actually coming true. Okay, so the model assumptions here. So basically, very simple thing. I almost hesitate to call it a model. Basically, we do slow freezing where we have the freezing is sufficiently slow to be in thermodynamic equilibrium, as opposed to a kinetically controlled flash freezing scenario. And this basically means that the order in which minerals crystallize as the solution is cooled is simply determined by the phase diagrams. We did not consider the formation of mixed salts. By that I mean more than one cation or anion in the lattice. For example, we don't consider things like sodium magnesium chloride 3. This exclusion was based on experiments that I hope to see published one day, showing that such salts did not form when we were looking at freezing tertiary brines of these species. So the upshot of this is sort of this flow chart of mineral formation as temperatures decrease, and I'm not going to go through this in a whole lot of detail, but just basically as things freeze, different species will form, and which branch you go down is then determined by relative concentrations within the solution. And like I said, after going through this exercise, we did experiments, poked at it, and showed that that it basically worked under this assumed conditions. All right, we then got some new experiments where we started using X-ray diffraction along with Raman spectroscopy, looking at these same brine systems over, again, a range of concentrations, but more importantly, we began looking at different freezing rates. And the reason we're looking at freezing rates is because we want to explore the impact that the freezing rate had on the mineral formation in order to simulate possible resurfacing mechanisms on Europa, where, for example, a flash freezing scenario might be relevant to a case where ocean or fluid or material is being thrown out into space in a plume, freezing really quickly and then falling back on the surface, versus something where things might freeze slowly, for example, fluid freezing out on the bottom of the ice crust and then somehow being, convected up to the surface where it could be seen. So again, trying to keep our experiments simple, we started looking at aqueous solutions in which concentrations of sodium and chloride ions are exactly twice those of magnesium and sulfate. The idea here was to limit the number of products that were expected under slow freezing conditions to only two, namely mirabolite and magnesium chloride dodecahydrate. So then the presence of other hydrated minerals would indicate a departure from this kind of slow freezing condition that we've been working in. I won't go through this too much here. Sorry, I'm getting these notifications popping up on my computer. All right. The table here shows a range of samples, different concentrations and freezing conditions we looked at. But what I wanted to show here are more the lab pictures. So again, we have the Raman spectrometer on the top right, but the first time showing is this XRD instrument on the bottom right. The XRD is way in the back of the lab there, but in the inset, you can see kind of a zoom in on where the sample is. So there you have the XRD goniometer, which is holding the sample capillary, which is then in the flow of a cryostream, which is essentially a cryogenic flow of N2 gas that's used to control the sample temperatures. All right, some results from this work. Okay, so these are Raman spectra of a diluted brine at 100 Kelvin. That was taken both after slow freezing and flash freezing conditions. The teal trace is the slow freezing sample. And if you look at sort of the inset where we zoom in on the sulfate symmetric stretch region, you see a nice characteristic Raman signal of mirabolite. Comparing that to the flash freezing, you see the red trace, which is that sulfate feature is kind of, it's broadened out and it's shifted to the left. And you can see that it matches very well with the control spectrum we have of magnesium sulfate glass. So what we see is that when we're flash freezing, the magnesium sulfate is forming in this vitreous or glassy state. If you look over sort of near 3,500 wave numbers in kind of the water region there, we see evidence of mag chloride in the slow freezing experiments. And that signal again disappears when we look at the flash freezing case, which again suggests that the mag fluoride is forming in sort of in a glassy state. Here we have some XRD data, and this shows patterns of molar brine that's been flash frozen at 100 Kelvin, and then the same sample after annealing at 200. So if you look at the blue trace, this is the flash frozen right before we do any annealing, and you can see it's very flat and featureless. So this indicates a lack of crystal structure in the sample, which supports our idea that we're forming these materials in glacis or vitreous form. If we then bring it up to 200 Kelvin for some time and let things kind of arrange into a more favorable arrangement and cool it back down, you see that all these features then start popping up from the sort of expected materials, so sodium sulfate and magnesium chloride. All right, so this has some implications in terms of looking at things on Europa. So if first of all, glassy materials, or from this work specifically hydrated magnesium-bearing salts, could be encountered on Europa, and this is potentially important because the presence of glassy materials may either hinder the detection or even hinder the identification of salt minerals. So it's something to be aware of. But then the question comes up, so why else might we be interested in this in vitreous salt hydrates on Europa? Well, it turns out that vitreous phases are known to protect cellular structures from physical damage that can occur during crystallization. So if microorganisms are in fact present in the subsurface ocean, you can imagine a scenario where they're entrained in glasses formed by brines that are erupted in plumes, for example, and deposited on the surface, where they could be preserved and potentially even remain viable. And I think the idea of finding a viable microorganism on Europa would be pretty neat, and I think really, strong evidence that we're seeing life elsewhere in the solar system. Okay, so this idea that there's a potential for preservation in glasses is not something that we necessarily came up with. It was first noted, to my knowledge, back in 2014 by Toner et al., who talked about the preservation potential of glasses when they were looking at the formation of glasses from slow cooling of perchlorate solutions relevant to Mars. Later in 2021, Fox, Powell, and Cousins also made this suggestion when they were looking at glass formation by flash freezing of putative Enceladus ocean fluids. Okay, anyway, when I'm thinking about all this, sort of three questions come to mind. The first one is, if we think that glasses could form on Europa, then how likely are they actually to form on Europa, given the potential emplacement mechanisms that could be there? So to look at this a little bit, we did a series of experiments where we looked at freezing rates. It's basically trying to understand how slow can the freezing occur and still form glasses. This, again, like I said, this relates to what emplacement mechanisms could be consistent with glass formation. The next thing to ask, or that I ask myself, is, okay, if we can get glasses forming, how long will they last? Do they just get on the surface and then transition to a crystal right away? So to look at that, we did kinetics experiments on this glass to crystalline transition. And then finally, if you have glasses on the surface and they stick around long enough to be relevant, do they actually salt hydrates relevant to Europa actually have this preservation effect on microorganisms? So we then did experiments that compared viability of microorganisms that have been frozen in both glassy and crystalline salt hydrates. All right, first the freezing rate experiments. So here we took small drops of salt solutions at various concentrations, pipetted them onto a glass slide at room temp. These were mounted within the cryo stage of the Raman microscope. We cooled everything down at various fixed rates down to 100 Kelvin, and then examined the samples with Raman spectroscopy to determine whether we had formed glass or crystalline form. Doing a bunch of these experiments then enabled us to determine the minimum freezing rate that results in glass formation, or subsequently the maximum freezing rate that results in crystalline salt hydrate. So here's some data that we got from this experiment. These are Raman spectra of frozen 2 molar mag sulfate brines at 100 Kelvin. If you look at the inset where we zoom in on the sulfate region, sulfate symmetric stretch region, we see that the blue trace, which is the flash frozen sample, shows a broad feature that's characteristic of glassy mag sulfate hydrate. And whereas the red trace, which was from a sample cooled down slowly at 20 Kelvin per minute, this shows a sharp feature that's characteristic of crystalline mag sulfate, or specifically meridianite. And from these types of experiments, we show that at the 2 molar solution was able to form glasses with cooling rates as low as 27.5 Kelvin per minute, whereas if we reduce the concentration, we were able to see that you see glass formation with cooling rates as low as 11 Kelvin per minute. So this is sort of a summary of all the freezing rate experiments we did, just the different species, concentrations we looked at. And basic takeaway here is that, given the right conditions, we were seeing glass formation with freezing rates as low as on the order of 10 Kelvin per minute. Okay, a couple of observations to note in relation to these experiments. Crystalline hydrates form at slower cooling rates than their vitreous counterparts. Solutions with lower ionic concentrations form glasses at lower cooling rates, and glasses form much more readily in samples with magnesium cations than those with sodium cations. Okay, on to the kinetics work. Here again, we took small drops of 2 molar mag sulfate solutions, put them on a microscope slide, cool them down to 100 Kelvin quickly at 50 Kelvin per minute. This then produced the salt in a glassy state. We then rose the temperature quickly at 50 Kelvin per minute to whatever given temperature we were going to examine the kinetics at. Here again, we look at the sulfate symmetric stretch Raman feature. We monitored that as a function of time to record the transition from glass to crystal. This transition again is identified by the change in this broad sulfate feature, which is the blue trace in the figure in the upper right, and the sharp, slightly shifted sulfate crystalline feature, which is the red trace. All right. So basically, we then got line shapes for the glass and crystalline sulfate features determined from control spectra, and these were fit to the data taken during the transition from glass to crystal, and this enabled us to get a crystal population fraction. And there's an example. This figure shows an example of one of those fits. So at each temperature we looked at, then we were able to get crystalline fraction plotted versus time. An example is shown to the right there, and fitting an exponential curve to that data, then we were able to pull out a rate constant for the reaction at that temperature. Now the rate constant, the temperature, activation energy are all sort of combined and described by the Arrhenius relationship. Now, this then meant that we could plot the natural log of the activation energy versus 1 over T, and then fit a line to that data, and then extract an activation energy from the slope. Okay, the result of this then gave us an activation energy of 60 kilojoules per mole, just to make sure we're not out to lunch here. This is in fact on par with the crystallization of amorphous solid water, which in the literature I see values up between like 60 and 77 kilojoules per mole. But anyway, what does this mean for Europa? Well, at 100 Kelvin, you can imagine sort of a characteristic energy available to molecules on the surface being given by RT, which is about 0.8 kilojoules per mole. This means that the activation energy is like 72 times that. So we can imagine that it's pretty hard for this reaction or for the crystallization to proceed spontaneously on Europa. Poking at this a bit, if we think about what the lower range of our uncertainty, we can get an activation of 51 kilojoules per mole. So that's sort of the lowest activation energy that the data, will support nicely. That's still 60 times RT. Another way of looking at this, if we use that plus our fitting results, the Arrhenius relation, we can calculate what the rate constant is, and therefore a characteristic time constant for this reaction at 100 Kelvin. And it turns out that that's 38 million years. So that's on the order of the surface. Of the surface age. So I think we can safely say that if this is formed on Europa, this glassy mag sulfate is not going to just spontaneously crystallize very easily. A couple caveats to mention is that the results, of course, are not taking into account effects due to like ion bombardment or any other radiation experienced on Europa. It also assumes that the Arrhenius relation is valid over the temperature range from experimentally accessible temperatures to those found on Europa. And I should point out that what I mean by what defines what was experimentally accessible was at the upper limit of temperature, the crystallization happened so fast we couldn't monitor it. It just, we looked at it and it just boom went and crystallized. Whereas at the lower temperature end, things happen so slowly we just never saw things crystallize. Okay, on to the viability experiments. Here, and excuse my pronunciation, we looked at Pseudoalteromonas haloplactus, which is a motile bacterium found in Antarctic coastal seawater. This is both a psychrophilic and halophilic organism, meaning it likes both low temperatures and high salt concentrations. And so we chose this due to as a potential as an analog to a potential Europan microorganism. Also for practical reasons, it's readily available and it's safe to work with. Okay, here we had these salt solutions with known concentrations of the organism, put them on microscope slides in the cryostage. We froze things down at different rates to either get vitreous or crystalline salt hydrates. We confirmed what state it was in using Raman. Then we quickly thawed samples at 290 Kelvin and then recovered them with cultivation and colony forming unit screening to assess the viability, and then did scanning electron microscopy to look at the morphology. So we did three kinds of samples we worked with. We did control samples where everything was kept at room temperature throughout the experiment, and then we did a set of samples that were cooled quickly to 100 Kelvin at 50 Kelvin per minute, resulting in the glass hydrate. And then we had samples that were cooled slowly at a Kelvin per minute until we reached about 250 Kelvin, where we held the temperature steady, waited until we saw the sample solidify. We then confirmed that we had crystal form with Raman, and then reduced the temperature down to 100 K. All right, let's do how many time. Okay, I'm doing okay. Samples were then thawed and recovered, and cultivation and CFU screening showed significantly more viable organisms in the vitreous samples over the crystalline. And you see that in the chart to the right, where the room temperature samples are shown in blue. We have the glass ice treatment, which you see a reduction in viability, but then you see another significant reduction in viability while you go to the crystal samples. So you see, basically, we have a statistically relevant preservation effect of the organisms in glass versus crystal. So here quickly are some scanning electron microscope images. On the left is the room temperature cells. These are bright, inflated, lots of prominent curvature, and this indicates that most of these cells have retained intact cellular membranes. If you look on the right, that's the crystalline sample where nearly all the cells appear to be deflated with lots of cytoplasmic release indicating cell lysing. And then the glass sample is is the center, where we see sort of an intermediary between the room temperature and the crystalline treatments. Upshot of all this is that I think we can safely say that these results support this idea that vitreous salt hydrates can promote the preservation and viability of organisms upon freezing of relevant solutions at Europa surface temperatures. And I'll just throw up my acknowledgement slide. This work started with funding through the NASA Astrobiology Institute, the Icy Worlds node, and has continued under JPL's Research and Technology Development Program. And with that, I'll end there.
Thanks so much, Paul. That was really interesting. Thanks, everyone. We're obviously at the hour, but we have a couple questions coming in, and I do want to we'll start off with Xinting, since we have a few of those here already. And so Xinting, the question comes in. Do you have any expectations on how thick a tholin or surface deposited material in general layer should be on Titan's surface?
That's a good question. I think the earliest paper that talked about that was like Jonathan Lee, 1983, something like that. But I think on the orders of 100 meters ish. So we're talking about. So actually before Chatain, right, we think Titan is covered by a global ethene ocean, because ethene is the most abundant photochemical product from methane photochemistry. But yeah, like a mixture of all these different things, like ethane and more complex hydrocarbons. But yeah, like 100 meters on the order of that, not kilometers. Yeah.
Okay.
So that's converting all the methane in the atmosphere to the surface material.
Gotcha. Okay, and one other question. What are the next tholin properties that you'd like to cross-compare with your upcoming work? You did the, I guess, the dispersive surface energy and polar surface energy, and you're going to keep working on this, it sounded like.
Yes, that's another great question. So we're funded to do electro property measurement, so dielectric constant. But we're also working on mechanical properties on the side, which is not funded. So if you see our proposal, please give us a positive rating. But the electro properties and surface properties can actually be linked to some of the existing Cassini-Huygens measurements to help us understand which tholin is better analog. So that's why we got funded to do those two. But Dragonfly will be interested, I think, in mechanical properties as well. That's what we're doing right now. We got 22 samples from collaborators in the past months, so exciting time.
Great.
Yeah, thank you so much for the questions.
And we have a couple coming in for Paul, so we'll switch gears for a second. Paul, your slow freezing experiments of the sodium chloride sulfate magnesium mixtures match with the salt precipitation sequence predicted by the aqueous geochem software packages like FreezeChem, and I think it's pronounced Freak.
Yeah. So the easy answer is yes. In that paper, we sort of compare how things, fell out against other models. Of course, our model we were considering a very, very simple sort of solution. The things that I was looking at comparing it with were a fair bit more complicated in terms of species present, but generally speaking, it was consistent with what we compared to.
And I guess I have a quick question, Paul. There's I liked your slide of showing all the people working out the math in the middle. It does seem quite complex. So is there a particular sort of detection or clipper measurement that you think would really kind of unravel the story? If something is detected, will it really help lead back to that interior ocean composition?
Well, that's what we're hoping to do eventually, but of course, it's the real world's way more complicated than anything that we've been done so far, right? We've been concentrating on relatively simple compositions to start with, right? So, a real ocean probably is going to have a lot more stuff in it to begin with. And I think the main complicating factor that we haven't began to poke at yet is the radiation environment and how that changes things and, muddles things up potentially.
Gotcha.
But we got to start somewhere, right?
Yes. Okay, and one, I guess, or two kind of combined questions about the microorganisms. So, will slow freezing and flash freezing of the ices affect the microorganisms? And then also just quickly, when you say halophile, is it salt loving in general or specifically sodium chloride?
So the organism that okay, so first of all, let me preface this that I'm not a microbiologist, and so the microbiology expertise comes from Seth Parker, but I'll try to answer. Yeah, the organism we're using was from Earth, so that would be specifically as sodium chloride. It would be native to a sodium chloride environment. Sorry, what was the other question was?
It was slow freezing and flash freezing of the ices affect the microorganisms. Or how will that be different?
Oh yeah, well, I'm not quite sure what we want to get from that, but basically, when by flash freezing it, we were able to form the salts in that glassy state versus the crystalline state when we do it slow. And I don't know what to say other than the viability was significantly higher when we were able to form the salts in the glass form versus crystal. Not sure I answered that question or not.
I think that's it. Yes, it is the slowest freezing leads to the crystalline form, right? And that's going to be the detrimental or more detrimental form.
Right.
Okay, well, so we're coming up 10 minutes past, and I don't want to keep everyone too much longer. And we've hit. Let's see, maybe we have one more question. But I think we've hit the moment here. So thanks again, Xinting and Paul, for really excellent talks. Sorry I started the recording a second late, but most of this talk has been recorded and will be up on the YouTube channel. And stay tuned for episode 3, which will come up in early March. And thanks again for your attention. Bye, everyone.